All right, so far in this course we've learned about two major derivative rules. The first one was power rule, and the second one was product rule. So today we're going to learn about quotient rule, and quotient rule essentially allows us to find the derivative of what we call like the division of two functions or the ratio of two functions. So if I have something over something else, I'm going to apply quotient rule. So you can kind of use this little definition here, but I prefer to just use the chant. So derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Okay, so we'll consider obviously the top or the numerator to be the top. This is going to be the bottom when we use the chant. So when we go to find the derivative of something like a, we're using quotient rule. It's the ratio of two functions, one function over another function. We're going to find the derivative of the top. So I'm actually just going to show you the top prime times the bottom minus the top times the bottom prime over the bottom squared. Okay, so derivative of the top. What's the derivative of 3x squared plus 2? Grayston? 6x times the bottom just as it is, kind of like we do in product rule, minus the top just as it is, times the derivative of the bottom, derivative of 5x minus 4, 5, all over the bottom squared, so 5x minus 4 squared. Okay, we expand and simplify the numerator just because we don't usually like to have like separate multiples like this that are being subtracted. So I'm just going to expand out the top, and just in case sometimes we might be able to like reduce a little bit further, so we do that if possible. So we'll get 30x squared minus 24x. I'm going to distribute the 5 and also the negative into both of these terms. So you'll have negative 15x squared minus 10. And then just gather up any like terms. Okay, if this guy were factorable up here, the numerator, I would factor it just so that we can, like you're going to see that we further analyze these graphs in Unit 2. So it helps with further analysis of the function. It also may help us just like further reduce the function a little bit. So factor if possible. I don't think this is factorable or common factorable, so we'll just box it up. Grayston? The bottom is already in fully factored form, so it's already in fully simplified form. The top has a subtraction between, so I want to expand and simplify and gather all like terms together. No. Okay, factored form is simplest form, so if you already have something that is like fully factored, you don't need to expand it out. Okay, any other questions on that one? Okay, let's take a look at the second one here. I might write this as x to the half, just so we can find the derivative a little bit more easily. All right, so r prime at x will be derivative of the top, which is 2, times the bottom just as it is, so x to the negative, or x to the positive half, minus the top just as it is, times derivative of the bottom. So for derivative of the bottom, we're bringing down the half and subtracting 1 from the exponent. So when I do half minus 1, I get negative 1 over 2. Okay, all over the bottom squared. Yeah.
Bottom squared is x. Yeah.
Yeah, so I'm going to simplify that in the next step here. Okay, yeah, we're essentially squaring a square root, so we'll just be left with x on the bottom. And I'm just going to just kind of like do a little bit of work distributing the negative in and also distributing in this half and the x to the negative half. So 2 and the half part will cancel each other. X, maybe I'll just write x minus a half there. And then half of 8 will be 4, and we'll still have the x to the negative half. One minus a half is positive half. So we'll have minus x to the half, and I'm going to write this as half on the bottom. Kristen?
How come we don't move it to just for the x's, the 4 over x half?
Why don't I move it? Oh, gotcha. We can't do that actually because this is the only single term that has that x to the negative half. If it were x to the negative half times that entire bracket, I could definitely do that and just move it down. But because it's only part of one term, I can't move it down below all of those terms all at once. Good question though. Okay, so 2x to the half minus x to the half is just 1x to the half. So I'm just going to write that as x to the exponent half. Okay, and actually maybe we'll just write these as square roots. And we do need to clean this up just like a little bit because we don't usually like fractions inside of larger fractions. So what I would like to do is just take this numerator and multiply both terms by root x so that the root x here and the root x here will cancel when I distribute that in. But I must also do that to the bottom. So I have to multiply the bottom as well by root x. So we're going to bring this in to both terms. Root x times root x for the first term is just x. And then the whole point of bringing this one into this term here is so that root x and root x will cancel. So when I bring that in, I'm just going to be left with 4. So it'll be minus 4. Okay, and then the last thing that I'm going to do is just gather these two x's on the bottom. So we do have a root x on the bottom, but if you write that as x to the half, we're just going to gather these two like bases here. So it will be 2 over 2 plus 1 over 2, and that gives us 3 over 2. Okay, remember exponent rules, keep the base, add the exponents. So I'm adding x to the 1, so 1 plus a half, that gives us 3 over 2. Emily?
When we have the exponent, do you want us to change it back to like root?
Yeah, so I think you'll see in like some of the worksheets, some of them change it back, some of them don't. So you can express this just as like the square root of x cubed. Either one of these answers for me is fine. Okay, can I clarify any like steps in particular here? Is anyone confused? How did you get from this to this? Kaylee?
If you were to like, instead of like bringing in root x, and you just times that whole thing, or actually never mind, that would work. Never mind.
You could actually, instead of bringing in a root x, you could flip and multiply, like think of this as x over 1 and flip and multiply. You would get the same thing down here once you do that. Yeah, well, you would get the same thing after you like flipped and multiplied and found a common denominator. So I think this is probably the more efficient way to go about it. Okay. Let's try another.
Wait, sorry, this is Kayla.
Yep.
So would the same thing happen, what if it was like, I don't know, like cubed root x to the power of like 4? So you do the same thing, take the cubed root of x to the power of 4, this one, like cancel it out.
Yep.
Okay.
Just multiply like by itself or whatever.
Okay.
Yep. Okay, let's try this one out. So g prime at x, derivative of the top, which is 6, times the bottom, minus the top, times derivative of the bottom. What's the derivative of x cubed plus 4? 3x squared, awesome. All over the bottom squared. Okay, expand and simplify your numerator here. I'm going to bring the negative and the 3x squared into that second term there, so I'm going to do that all together. And then just gather your like terms. And if possible, you will factor or common factor. I'm seeing a common 3 in all of these values on the top, and the first term happens to be negative, so I'm just going to remove a common negative 3 from each of those terms. And that will be fully simplified. Okay, couple of the biggest mistakes that I see when people are using quotient rule, they get confused between quotient rule and power rule, and they put a plus here instead of a minus. Or I do this actually all the time, is I forget to square the bottom. So those are just like a couple little things to look out for as you're doing these questions. Any questions on this one? Can I scroll?
I have a question. This might be silly, but what are we, like, what are we trying to find using this? Like, why would we use this over top of, like, the other?
Like the other rules that we've used?
Yeah.
So this one is specifically for like if we have a division between like two functions, this is when we have to apply this particular rule. So like product rule, for instance, I would have maybe something more like this, right? So that's when I would apply product rule.
Okay, that makes sense.
Okay, determine an equation for the tangent to the curve y equals x squared minus 3 over 5 minus x, where x equals 2. Okay, so equation for the tangent, I need the slope of the tangent to start, which means I need the derivative of this function. Yeah, go ahead, Grayson.
Can you find like the first derivative without simplifying it, or just putting x into that equation?
Yep. Yep, so we'll find the first derivative. So we're going to do derivative of the top times the bottom minus the top times derivative of the bottom over the bottom squared. Oh, and I almost forgot to square it. Okay, normally I would say at this point, because we're just trying to find an equation for the tangent line, we could plug in x equals 2. Because we're working with this for the first time, we're gonna just take a couple extra steps to express this in simplified form, just so that we can practice. But at this point, you really could just plug in x equals 2. But again, let's just make sure that we know how to express this in the proper format. So I'm going to bring in the negative and the -1 for the second term. Okay, this one doesn't take too long to simplify anyways, so. Okay, so this would be, with the negative common factored out, this would be kind of like if I asked you just find the derivative, this would be how you're expressing that derivative. Okay, again, certainly if you're doing other questions, you can go from this and evaluate where x equals 2. Okay, so we are going to evaluate, this is the notation that we'll use when we're doing dy over dx. We're evaluating dy over dx when x equals 2, and we'll sub in 2 for x. So positive 13 over 9. Correct me if I'm wrong. Yep, perfect. So this is the slope of our tangent when x equals 2. That's what we just found. That's what the derivative helps us find, right? And what else do we need for these types of questions? Like if we're trying to find the equation of the tangent. Grayston? We need the y coordinate for where x equals 2. So we need to plug in, we need to find a point on the tangent. And we'll find that from the original equation. So we're just going to sub in 2 into the original equation. Getting 1 over 3 here. So our point would be 2, 1 over 3. Okay, almost done here. So our last step is basically just now to find the equation of the tangent line in mx plus b form, y equals mx plus b. So I know the slope of the tangent is 13 over 9. And we know a point on the tangent to 1/3. Okay, so I'm going to just create a common denominator here as I move this fraction over to the left-hand side. So I'm going to write this as 3 over 9 minus 26 over 9. And we'll get negative 23 over 9 for b. Okay, and then you're just going to sub that back into your equation. Okay, so essentially, like all of these types of questions, they followed the same format. Use the derivative to find the slope of the tangent. You find a point on the tangent, plug that point in and the slope in, and solve for b. Okay, any questions for this one? Can I scroll? Okay. Last one, we are going to determine the coordinates of each point. So when we say coordinates, we mean xy coordinates of each point where the tangent is horizontal. So when we say tangent is horizontal, that means where slope equals 0. Okay, so I'm going to find the first derivative, and I'm going to set that equal to 0 and solve for the x's that make that true. So we actually already have found the first derivative of this function. We found it above, so obviously we're not going to do that again. So I'm just going to use the derivative that we found above. That was in part B of example 1. It was x minus 4 over x times, or x to the exponent 3 over 2. Or square root of x cubed, whichever you want. Okay, so I'm just taking our answer up from part 1b, and we're going to set it equal to 0.
So during like a test or an exam, if we do have a question we want to answer, can we write that?
Yeah. Okay, when you are solving for where a rational function or like a fraction of two functions is equal to 0, it will always be equal to where the numerator is equal to 0. Okay? Where the denominator is equal to 0, the function should be undefined, but where the numerator is equal to 0 is actually where that whole function will be equal to 0. So really what we want to solve is where x minus 4 equals 0. So when does x minus 4 equal 0? Yeah, so here x equals 4. Okay, you can actually also see on your graph over here that that looks approximately where your slope of your tangent is going to be horizontal. Okay, and then your job is to find the y-coordinate as well. And we're just going to make ourselves a little note.
So it should always be between
Okay, so it's equal to 0 where the numerator equals 0. Okay, so just evaluate h at 4, and you'll have the y-coordinate for that point.
Do you always want us to do that even if there's a graph there?
Yeah, I basically just put the graph there so that you can see what's going on visibly, but you probably won't have a graph for a question like this. Essay?
So if the question says each point, if there were two like factor brackets or two different ways.
Yep.
So we do each.
Yep.
Also, why is it the start of
Because I'm evaluating h at 4, and the original function is,
the original function?
yeah,
Is that?
that's it. Okay, any questions on that one? We're okay?